Hello, I'm your host, Dr. David Urban, and I will be guiding you through Brown and Poon's Introduction to Organic Chemistry, 6th edition. The slides were downloaded from the Wiley Instructor Companion site and are copyrighted by Wiley. The commentary is my own. I have divided each chapter into smaller sections to make it easier to view on a wide variety of platforms. So let's begin. We will continue with Chapter 1, Part 5. Okay, in the previous video, we saw that we could form a tetrahedral structure by having 4 equivalent bonds, okay? Now, if we think about that, how is that possible? Because when we look at that second energy level, we have an s orbital, which is spherical, and we have 3 p orbitals, which are dumbbell shaped, okay? That doesn't make 3 equivalent bonding opportunities, right? So there must be something else going on here. And so what we're going to see is that we're going to have to hybridize or blend that S and those P's together to get 4 equivalent orbitals. All right, let's go back and start looking at our shells again. Our first shell is spherical and is completely encompassed by our second shell as we start adding electrons to it. So all we care about are the electrons in that 2 energy level, okay? Now, when we look at our P's, they again are this dumbbell shape. One is in the x-axis, one is in the y-axis, and one is in the p-axis here. Now, that should give us a place to bond 3 things in those 3 different directions, and those bonds would be 90 degrees apart if we only use the p orbitals to do the bonding. So the fact that when we have that tetrahedral structure, it's 109.5 degrees apart means we've done something. We cannot have these pure p orbitals doing the bonding. So what do we have happen right here? So when we make a covalent bond, we overlap 2 orbitals. And if they're equal orbitals, like in the case of hydrogen, we only have a 1s electron and a 1s electron, and they overlap to form this covalent bond. And that is nice and simple. Once we get to the 2 energy level, we have to worry about whether we're bonding to an S or a P. Okay, so what happens is instead of having an S bond and then the 3 P bonds in different angles, what we end up happening is we hybridize the orbitals of S and P together. When we do that, that gives us different shapes, okay? So we're gonna take that s orbital, move it up a little bit in energy, take those 3 P's, move them down a little bit in energy, and if we make them all equal, if we're using all 4 of those orbitals together, we have an sp3, because there's 3 P's, hybridized, and they'll give us 4 equal orbitals. Let's say we don't use all 3 P's, we just use 2 of those P's and 1 of those S's to give us 3 equal orbitals. If we have 3 equal orbitals, that will give us 3 equal bonds. Ooh, think trigonal planar right there. And then if we take 1 S and 1 P and blend those together, we'll end up with that 180 degree bond angle we have. Okay, so what does that look like? Let's take a look at what that would look like here. So in the case of taking an S orbital and blending it with 3 P orbitals, you're going to take some of that spherical character of that S and blend it with that dumbbell shape, making one side of that dumbbell slightly bigger than the other side, or bigger than that other side. And then that means we have that small lobe that has less electron density in it, right? So the big lobe of it is the one that dominates the electron repulsion. So now we have 4 of these big lobes, and the best way we can spread 4 things out in space is to give us that 109 degrees tetrahedral shape. So if we took the s orbital and all 3 p orbitals and blended them together, that each of those orbitals now has 25% s character and 75% p character, okay? So what would it look like if we started moving those around and we actually bonded things to them? If we started bonding things to them, if we had 4 equal bonds to them, we would have those 4 equal bonds be at that tetrahedral shape around there. Okay. Now, if we only had 3 things to bond to it, like in the case of ammonia, where we already had 5 electrons in the outer shell of nitrogen, we would end up with a lone pair. And that lone pair would then be in that sp3 hybridized orbital and give us a pyramidal molecular shape, but the orbitals will still be in that tetrahedral shape. So that's what's forcing those 3 hydrogens down to give us that pyramidal structure. Okay. And the same thing happens when we have oxygen. It is also sp3 hybridized, and it has a total of 2 lone pairs. Those are taking up 2 of those tetrahedral electronic configurations, and the 2 bonds to hydrogen are the other 2 of the tetrahedral, meaning the molecular shape is bent. But if we looked at the electrons, that would give us our tetrahedral shape. Okay, so now that we show that we can blend those together, let's talk about the different types we have, okay? So I talked about what the shape would look like if we had the sp3, where we have 1 s orbital and all 3 p orbitals are blended together. That gives us 4 equivalently shaped orbitals, okay? So that's what gives us our tetrahedral shape, okay? If we only take 2 of those p orbitals, that means we have 1 s orbital and 2 p orbitals. That would give us 3 equivalent spaces plus a p orbital that we haven't touched yet. That means that p orbital is going to bond like a p orbital. It's going to be dumbbell shaped. It is not going to be it's not going to change the shape of the molecule. So if we have an sp3 hybridized orbital, that's going to make it a trigonal planar shape with those orbitals. That's how they can evenly spread out. And if we use 1 of the s orbitals and 1 of the p orbitals, that'll give us our linear type combination, but we'll still have 2 p orbitals that can bond as p orbitals, okay? So when we have these configurations, we have 2 ways to do bonding, where we have the electrons from one atom overlap with the electrons from the other atom. And when we do that, we have what we call pi bonds. Notice this should, we have a sigma bond. This should be the sigma figure here. When we have a sigma bond, that's a direct overlap of an sp3 or sp3 hybridized orbitals, or maybe an sp3 and an s orbital. We have direct overlap with that, giving us our sigma bond, okay? Now, if we were to have an overlap with just a p orbital all by itself overlapping with the p orbital, that would be above and below the plane, and that would be what we call a parallel overlap or a pi orbital. So these are pi orbital overlaps give us pi bonds. Those parallel overlaps give us pi bonds. Direct overlap give us sigma bonds. Okay. That being said, let's continue on with what our sp2 looks like, okay? Now, when we have 1 s and 2 p's, that makes it a little more S-like, a little more spherical. So notice in an sp2 hybridized orbital here, the dumbbell is more pronouncedly, bigger, okay? And so we have those 3 of these really oversized dumbbells that we have to spread around as far apart as we can. And so we can spread those out in that trigonal planar configuration. We have 3 things in space gives us at 120 degrees. But we still have, because we've only used 2 of the p orbitals, we still have a p orbital somewhere, okay? Now, what happens is the p orbital is going to be sticking in and out of that plane above and below the trigonal planar structure left by those sp2 hybridized orbitals, okay? So you think about it as your sp2 hybridized orbitals are on this plane, and now you have a p above and below that plane where you can bond to, okay? So that means this one that's in the plane is going to do the direct bonding, the sigma bonding, and that p orbital above and below the plane is going to do this parallel orbital bonding. Okay, so let's take a look at that, okay? So, like I said before, the ones that are hybridized here are in this trigonal planar structure and give us our sigma bonds, and all of our sigma bonds are in this plane created by that 120 degrees evenly spaced around. And these p orbitals are above and below that plane. They are parallel above and below that plane, giving us our pi bond, okay? So again, your hybridized orbitals give you your direct sigma bonding. Your p's overlapped parallel give us our pi bonding, okay? So here's another way to look at it. Here's the plane created by the molecules here, and this pi is above and below that, or that plane created by those right here. So this is the pi orbital and pi bond, and the rest of the bonds are direct or overlap or sigma bonds. Okay, so we don't have to have molecules actually bonded to them. We can have an sp2 hybridized atom that has lone pairs on it. When we have something like that, in the case of oxygen, when we draw our Lewis dot structure, we have two lone pairs on our oxygen here, okay? And the fact that we have three areas of electron density tells us we have a trigonal planar configuration with those electrons, okay? So that means that the carbon here is sp2 hybridized and has a p orbital available. And because this is trigonal planar, this is sp2 hybridized, and it also has a p orbital available to bond, okay? So all of the sp2 orbitals are going to be trigonal planar and give us this flat plane of sigma bonding. And these two remaining p's right here are going to be above and below the plane, giving us our parallel bonding here in blue, parallel bonding above and below the plane to give us our pi bond, okay? So now being above and below that plane gives us some reactivity, and we'll see that that's where all the reactions happen. But again, we have the sigma bonds form this planar flat structure, and the pi bonds are above and below that flat sigma structure, giving us our second bond, okay? So what if we only have one s and one p blending together to give us a hybrid orbital? What happens there, okay? What we see happen here is that the lobe is very extended. This is, again, half S character, half P character, which means the lobe is even bigger than it was with an sp2 or an sp3 hybridized orbital. So it's very large orbital, so that when we have those together, they are 180 degrees apart, okay? So when we bond two sp hybridized atoms together, they're going to be 180 degrees apart, and then the next bond is going to be over here. Let's put just hydrogens out here. So we have a nice linear molecule here. But again, we only used one s and one p to make this hybridized orbital. That means we have two p's available to put somewhere else, okay? So if these are in the plane of the molecule, that means that one p has to be outside that plane, outside this linear line here, and so we have it going in this direction here, and then the other p orbital is going to be 90 degrees apart from that, okay? Which means we have p orbital in the plane of our sp hybridized orbital, but we have one above and below that plane of the sp hybridized orbital. So if we were to take those and bond those, what would that look like? Okay. So in the case of acetylene, we have three lines in between the carbon and the carbon in the acetylene molecule. So the first lines that we see here, right here, the one line between the two carbons, the one line between the carbon and the hydrogen, those are our sigma bonds created by our sp hybridized orbitals, okay? Those are our first bonds that form. Now we have two p orbitals left, and so what happens to those is One set of p orbitals is going in the 90 degrees away from the linear portion of the molecule. And then the other orbital is going 90 degrees away from that as well, which means that we have the p orbital that's above and below the plane creates one pi bond here and here. And then the p orbital that's in the plane here creates a second pi bond. So that's the one back here, and the one up here creates our second pi bond, okay? So that means in acetylene, we have one sigma bond, one pi bond that's in the plane, and one pi bond that's out of the plane. So that gives us a total of 3 bonds between those carbons. And the only way we can do that is if we have one sigma bond that's sp hybridized, and then we have overlap bonds or pi bonds with the 2 remaining p orbitals. Okay. Okay, so to summarize there, if you have 4 things bonded to carbon, it is going to be sp3 hybridized, and it's going to have a tetrahedral structure or 109.5 degrees apart, okay? So things like ethane and anything else that has just 4 bonds to carbon, okay? If you have 3 bonds to carbon, that means your carbon is sp2 hybridized, okay? sp2 hybridized, you have 3 bonds to carbon, and it's going to be trigonal planar, and then you're probably going to have a pi bond somewhere, and it's going to be above and below that plane. That remaining p orbital is going to give you that pi bond available to it. Okay? If you have 2 bonds to carbon, that means you're sp hybridized. That means it's going to be linear, and that you have 2 p orbitals that will form 2 pi bonds. Okay, so when we think about the number of things bonded to the carbon, think about the hybridization. The hybridization gives you shape, and it tells you whether or not you're going to have pi bonds available to you in your system.